Hi, everyone. My name is Mike Valley, and on behalf of the Applied Technology Council, I'd like to welcome you to this webinar on the concrete structural wall recommendations in FEMA P-2208 NEHRP Recommended Revisions to ASCE 4117. This webinar is brought to you by the Applied Technology Council under a FEMA NEHRP Architect Engineer contract. If you haven't already, you can download the handouts using the link in the chat. We know that many of you are interested in receiving professional development hours for your attendance today. For those who registered and attend the webinar, a certificate documenting professional development hours will be sent by email within 4 weeks. If at any time during the webinar you have questions, please type them in the Q&A window that you can open from the Zoom control panel. We're planning to have a live question and answer session at the end of the webinar. Please submit your questions as you have them, rather than waiting until the end to submit them. We'll answer as many questions as we can, time permitting, at the end of the webinar. Our project sponsor, Christina Aronson, who is with FEMA's Earthquake and Wind Programs branch, is unable to join us today. I'll read the introductory comments that she's prepared. So this is from Christina. Hello, my name is Christina Aronson, and I'm a structural engineer at the Federal Emergency Management Agency's National Earthquake Hazard Reduction Program, FEMA NEHRP. It is my pleasure to welcome you to today's webinar, the third of three, covering NEHRP Recommended Revisions to ASCE 4117, Seismic Evaluation and Retrofit of Existing Buildings, FEMA P-2208. Today we'll be covering the background and studies of P-2208's recommended revisions to concrete structural wall portions of ASCE 41. To set the stage, FEMA has the goal of reducing the ever-increasing costs that disasters inflict on our country. Addressing the risk presented by our population of existing buildings, of course, is the most effective way of reducing the cost of future disasters. The National Earthquake Hazard Reduction Program, NEHRP, is composed of 4 agencies: NIST, USGS, NSF, and FEMA. As part of the statutory responsibilities under NEHRP, FEMA is charged with supporting the investigation of seismic technical design issues, the development, publication, and dissemination of technical guidance, design and construction guidance products, and support of model codes that are cost-effective and affordable. This report documents the work of a 5-year FEMA NEHRP project. FEMA submitted 35 detailed proposed revisions into the official ASCE 41 consensus standards process. FEMA P-2208 presents the submitted change proposals and commentary in addition to the results from the technical studies that informed the proposals. It's not intended to replace ASCE 41. FEMA values this partnership with the American Society of Civil Engineers and the important work it does to provide national consensus engineering standards for buildings. We hope you'll find this webinar useful, and we encourage you to let us know if you have any questions. We also want to thank the Applied Technology Council for managing this project and helping us deliver this session under a FEMA NEHRP Architect Engineer contract. Additionally, we thank Garrett Hagan for presenting here. He's been improving our treatment of concrete buildings on FEMA NEHRP projects and in other professional activities. The names and affiliations of all who contributed to this work are provided in the report. Without their dedication and hard work, this publication would not have been possible. The nation is safer from the next earthquake as a result. So that's the conclusion of Christina's introductory remarks. Now let me tell you about your presenter today. Our presenter is Garrett Hagan. He's a principal at Degenkolb Engineers, and he has over a decade of experience in existing building evaluation and retrofit. Garrett is a recognized expert in hazard mitigation and an active contributor in developing the state of practice for earthquake resilient structures through published papers, committee reports, and the development of ASCE 41. He currently serves in the following related committee roles. He's the chair of the SEOC, California State Existing Building Committee. He's the co-chair of the Southern California SEOSC Existing Building Committee. He's the chair of ACI 374 for performance-based seismic design of concrete buildings, and he's the chair of ACI Committee 369D for updates to ASCE 41 wall provisions. So now we can give our attention to Garrett and his presentation.
Thanks, Mike, for the introduction, and thanks for the opportunity here. I should maybe just add one correction on the different chair roles. I did pass the torch on the SEOC state level, but still the co-chair of the local SEOSC level, just in case folks are listening and anyone was confused on that. So not a big deal. So apologies, Mike. I should have probably updated that bio. But anyway, here's the agenda today. So the agenda for today's webinar is all around the technical background on the structural provisions for in ASCE 41 for concrete structural walls. So hopefully you are somewhat interested in concrete structural walls and you're in the right webinar. That'll be really the subject matter for today. We're going to talk through the classification of wall behavior after some background, really classifying whether the wall is governed by shear or flexure or other mechanisms. We're going to talk about updates to how we look at wall stiffness, and then we'll get more into the specific failure mechanisms, their modeling and acceptance criteria, and the technical recommendations that came out of this project for flexure, shear friction controlled walls, respectively. And then ultimately some final thoughts on how you might actually incorporate those into your model, some added recommendations on how you might go about analyzing in today's typical commercial software. After which we'll have some time for Q&A, so I'll try to wrap up in time for some of that. So some background, I think Mike already gave us a great background on most of this, but just so that it's clear, this project was intended to provide technical recommendations based on what was in ASCE 4117 and would influence what then would get ultimately approved in ASCE 4123. This document with NEHRP recommended provisions is very similar to what's been done traditionally for ASCE 7, but was done now for the existing building world for seismic evaluation and retrofit. And it's important to note that not all of the recommendations exactly went in as recommended from this document into the standard, but they really served as the technical basis for those provisions. And I think all of the change proposals that were recommended did end up in the standard in some fashion, maybe with some minor revisions from the committee as they went through the consensus process. But it was a really successful project in terms of providing value and technical recommendations to really progress the ASCE 41 standard. This project, as Mike mentioned, had a lot of contributors. It had the backing by FEMA to support some funding for this, and then the Applied Technology Council project executive was John Hines, and the project technical committee director was Terry Lundeen, and there are a lot of other folks that contributed. Some of the PTC members are listed there, and there were also the different working groups that had their own members that contributed to the particular technical subject matters. So of those working groups for the technical members that were developing this technical background, there were 6 different working groups. There were linear and nonlinear analysis working groups, foundations, concrete structural walls, which is the relevant one for today. There was a group that looked at the tier 1 and tier 2 procedures, as well as unreinforced masonry. There are 3 different webinars that came out of those working group technical backgrounds, like the one today. So the other 2 have already been presented for nonlinear analysis and unreinforced masonry. And then, as I mentioned already, and as you're hopefully well aware, this one is all around the concrete structural wall technical background for the provisions in ASCE 4123. And as I sort of alluded to already, there are a lot of proposals generated out of this project. It looks like in total we counted 35, and they were really all accepted through the ASCE 41 consensus process, granted with some changes, but it was a great success on developing technical background for that really influenced the progress of the standard. One other nuance to be aware of in terms of ASCE 4123, which is unique relative to the earlier versions of the standard, is that ASCE 41 has started to move in the direction of some of the new, new building standards that are out there. So as likely a lot of you are aware, ASCE 7 really dictates the loads and hazards that are to be considered for buildings. and then they point to more specific material standards for the capacities and local acceptance, strength reduction factors, those things for the individual materials, so concrete, steel, masonry. ASCE 41 has started to move that direction in a similar way, but not for all chapters. So it happened for ASCE 4123. There was the concrete chapter is now basically uh, the technical provisions are mostly handled by ACI 369, the committee ACI 369. And the same thing happened for the steel chapter, where there's a steel committee, AISC 342, who is now handling the technical updates on the steel provisions. So the way this works, there's a memorandum of understanding between the organizations, and ACI, and I'm involved in both. And ACI 369 basically develops all the technical provisions. They actually have their own standard, ACI 369.1. That standard was issued just before ASCE 4123. So there's a 2022 version of ACI 369.1, which ASCE 41 then adopts by reference in the concrete chapter. In general, the goal is to adopt that standard by reference and not really have too many substantive changes beyond that. But in this particular kind of first attempt at this organization, there were some really good technical changes that came out of this project for concrete structural walls specifically, and some others that were being balloted for concrete foundations in ACI 369. And they were basically all the way through balloting. They had gone through 3 different rounds, but 369 then went to public comment based on their schedule. It dictated having to do that. And so not all of those changes actually got into ACI 369.1 this last time around. So at the end of the ASCE 41 cycle for ASCE 4123, there was a big effort to pull some of those really key recommendations into ASCE 41 directly. So the way this version of ASCE 4123 works is that if you go to chapter 10 and open it up, it will say see ACI 369.1, for most of the provisions for concrete, but also see the modifications that are captured directly in chapter 10 of ASCE 4123. So where anything is written into that chapter 10 language, that would be the prevailing standard for ASCE 41. And basically it's just incorporating some of these technical recommendations that were, again, almost fully balloted in 369 to get in to be usable in ASCE 4123. The consequence of not getting those in would be waiting until ACI 369.1-28, which would then get adopted in ASCE 41 in 2029. And that was something that it felt like it was too far out. These were really important changes. So I was happy to see that these changes did get into ASCE 4123 by modification of the reference standard there. The background on this document, this particular document, FEMA P-2208, is that it really provides all the technical background for those changes. So you can only handle so much of the background in commentary. I think there is some good commentary that went into ASCE 4123, but this document provides a lot more extensive background on the databases that were used and the really all the background, the meat of what informed those final provisions that went into ASCE 41. So I would recommend that you look at this as a reference, especially if you're having questions on some of the background there on concrete walls and some of the other working groups I mentioned. There's some good substantive language there that would be valuable in understanding the intent of the provisions. I'll also note that right now there's an ongoing effort to update FEMA P-2006. So if any of you are familiar, FEMA P-2006 was provided examples of ASCE 41, primarily ASCE 4113, but then it had some commentary for ASCE 4117 as that was being issued at about the time that was published. This next version would then incorporate ASCE 4123 provisions and basically update some of those key examples based on these updated provisions in 4123. The goal is for that to be released late 2025, so late next year, and we're well on our way to working through some of those examples, and I think that'll be very valuable to see an actual worked example of how these provisions play out. The working group dedicated to concrete structural walls is listed here below. Wasim Ghanum was the team leader for this working group. And I'll also highlight Saman Abdullah. He was, I think at the time, a postdoc under John Wallace at UCLA, but his PhD work really revolved around collecting this database for concrete walls from all different sources. And then that database was really the vehicle or kind of the engine, I would say, that allowed for a lot of these technical updates. We had a large amount of data to actually dig into and look at. There's some more information on that here below. But without that data, I don't think a lot of this would have been possible. These would have been mostly judgment calls, which sometimes had to happen in the past based on lack of data. So that was a huge benefit to this project. So the first part of the agenda is really talking about wall classification. And if you all are familiar with ASCE 4117, you might notice that there's not really a direct statement that tells you how to determine whether a wall is controlled by shear or flexure. There are tables that tell you here are modeling and acceptance criteria for shear controlled walls and flexure controlled walls respectively. Uh, if you're a bright user and you're thinking about it from first principles, you could go in and figure out which would be the governing mechanism based on your demands and your capacities for each of those mechanisms. But really, there's no standard language on how to do that. And all that you might find is there's some recommendations in the commentary that tell you, hey, in general, based on aspect ratio of the wall or height to length ratio, you would generally expect, I think the number is like over a 3-to-1 ratio, you'd expect it to be flexure controlled, and really, 1-to-1 or thereabouts, you might expect it to be shear controlled. But there's really no standard language or direct provision that tells you how to classify a wall and therefore which tables should you be going to for that wall. So we cleared that up in these technical updates, and then ultimately what went in the provisions. And a lot of the background here informs how we cross-referenced what the ACI 318 equations might give you against the actual database that Saman and UCLA had developed. And it was helpful to understand as we make these technical recommendations how the actual database corresponded to what we might expect from mechanics and the equations that we have in our standards for concrete. One of the other questions that comes up for concrete walls is what happens when you don't have just a simple rectangular planar wall and you actually have an irregular plan cross-section or cross-section and plan. So on the left, you see this rectangular wall, and on the right, this sort of L shape. You can have all kinds of return wall conditions in real buildings, as any of you that have analyzed real buildings know. You might have T's or L's or C's or anything, any other letter in the alphabet that you might expect you could have. And the natural question is, do these two walls have the same performance? In ASCE 4117, there is really nothing to guide the user on how to judge a distinct performance between these walls. So generally speaking, I think the approach, and at least our approach in our offices, was to idealize the wall on the right there as two different walls, one wall that's going sort of left, right, or east, west in the plan view there, and then a separate wall that's going north, south, assuming that it acts sort of with the provisions that were really intended for rectangular walls. So we had a chance to distinguish that better based on these technical updates, and I think that's a valuable thing. There's actually a big influence that you have from that return wall, and it depends on the direction of loading, as you might expect as well, whether it influences strength in a positive way or a negative way. Strength is probably a more obvious one. The other really important thing that maybe is less obvious is the modeling and acceptance criteria, the deformation capacity, and that would be influenced in a different way depending on the direction of loading. So there are some recommendations on that came out of this technical background and this technical work. As I mentioned, there's a really large database that Saman and John Wallace and team had collected that informed a lot of these technical updates. There were, it looks like, over 1,100 walls, so well over 1,000 walls, and they had a variety of different conditions. We had flexure controlled walls in there with different failure modes, shear controlled walls with different failure modes. There are walls that, if you're familiar with wall behavior, were not really clearly shear or flexure independently, but there is an interaction at play, and some of those had sort of a failure mode associated with flexure and shear. And as I understand it, there is some data out there for inadequate lap splice walls, but those inadequate lap splice walls did not inform the technical updates that are covered here. My hope is that in the next cycle, we'll have more guidance on inadequate lap splices, but at this point, you're still beholden to the provisions in section, I think, in ASCE 4117, it was 10.35 or so, or section 3.5 in ACI 369. So for flexure controlled walls, as I mentioned, there are a number of different failure modes that one you might expect, but also that the database captured. So you might have crushing or bar buckling based on the compression side of the cross section. You might have bar fracture on the tension side, or you might have some of these other failure modes like lateral instability or other things. A lot of those were captured, and the nice thing is we were able to isolate those and understand how those influence the modeling and acceptance criteria recommendations coming out of this. Similarly, for shear controlled walls, there are actually different modes of shear failure. There can be diagonal tension, there could be diagonal compression where you really get a crushing of the concrete strut. And then the one that you may have always been aware of, but less people were explicitly considering, as I understand, is actual sliding at the base. So where you have shear friction sliding between the wall and the foundation interface, that is more explicitly covered now. Um, uh, that should be more clearly covered. Now, when I mentioned there's this interaction with shear and flexure, the reality is you can't always just isolate shear and flexure and have them act completely independently in a real wall. Even though we do that in most of our analysis, our commercial software that's available, we typically in our software would assume that there's a material that covers shear and then there's a material that covers flexure, and that those two materials are acting independently. The reality is they do have an interaction. So what we try to do with some of these technical updates is we recognize that, but is there a I guess a criteria or a bin of these data that you can say, hey, this is really governed primarily by the flexural actions, and at this point you can say we're gonna really call it a flexure controlled wall, and then under that, you know, we do something else. There's a lot of debate on how to approach this in the working group, recognizing that there is this gray zone, especially when you're sort of in between shear and flexure controlling, um, that it's tough to just say it's one or the other. So the way we went about that is basically, and this plot I think has a good visual representation of the different failure modes and where they fell on the vertical axis. Where you're basically looking at whether it was sliding shear or diagonal shear strength controlled. So the ratio of shear friction to diagonal shear strength, and then on the horizontal axis, it's really a question of the shear associated with flexural yielding. So the shear demand being on the numerator, and the denominator being the shear at flexural yielding. So it looks, you know, that probably sounds a little complicated, but the big thing is in the orange or yellow there, I guess it's more yellow, you'd expect those walls to be sliding shear controlled. the actual yellow dots were observed. So the actual observation of the wall behavior in the experiment was sliding at the base for those yellow dots. The red dots then are diagonal shear controlled, so you're not seeing sliding at the base, rather you're seeing a diagonal failure in either tension or the compression strut that I mentioned earlier. The blue dots would be flexure controlled, so truly vertical bars yielding and or crushing at the compression side of the end of the wall and flexure. And then the green there would be an interaction. Really, there's a combination of some of the flexural crushing or cracking that you'd expect in a flexure controlled wall, along with those diagonal failure modes in a diagonal shear controlled wall. And so those are green, and you can see those are scattered a bit more throughout, but especially in the region where you're kind of transitioning between shear controlled and flexure controlled. So the approach that we took, and you'll also notice, I'll point out that there are a couple, like just a handful of red dots that are slightly over that ratio of 1. So again, when you would calculate based on ACI 318 that it's shear controlled, versus when you would calculate based on shear ACI 318 that the shear associated flexural yielding is actually greater than 1. That's the vertical line that's going down the center there, or kind of going down vertically there. You'd expect if you're on the right, you'd be flexure controlled. If you're on the left, you'd be shear controlled. Some of those red dots are coming out because, in fact, they were observed in the test to be shear controlled. And the way we dealt with that, and also dealing with some of these shear flexure sort of interaction walls, is we said that we're not going to use just the flexural yielding strength to determine this. We're going to use the overstrength flexural capacity, basically the max flexural capacity you would expect in that backbone. If you drew out the flexure controlled backbone, you get yielding, and then you get some strain hardening and material overstrength. We're going to use that value that would be kind of your ultimate moment capacity. And if you look at the shear associated with that flexure capacity, are you expecting that your shear flexure controlled? And that helps us basically with more confidence that for sure we have all the shear controlled walls covered. And in general, you're going to capture more of those diagonal flexure shear controlled interactions. The idea is that if you call it a shear controlled wall and it was actually a flexure controlled wall, you're probably a little conservative, because the general modeling and acceptance criteria are lower for shear controlled walls. We expect less ductility out of shear controlled walls. Versus the other direction, we didn't want to call something a flexure controlled wall that was really governed by shear and be unconservative for the purposes of design practice and having something in the provisions. So ultimately, we ended up with this table that has this pretty well-defined criteria on identifying whether the wall is controlled by shear flexure or being sliding controlled at the base. So having shear friction as the controlling action. So I'll just point out too, with the shear friction controlled behavior, there are always shear friction provisions. There's some language in ASCE 41 that says that connections between concrete components are to be treated as force controlled. So if you were checking shear friction, you very often found that governed, and then you had to treat that action as force controlled. So it was really penal if you actually looked at it. I understand from speaking with some folks that not everybody was considering that mechanism, so they may have overlooked it, and therefore it wasn't a problem. But if you looked at it, it traditionally was a problem. So the benefit now is we have some actual recommendations on, hey, if there is sliding at the base that happens, this is how that wall performs. And it's not necessarily a force controlled action. It's not as though as soon as you get shear friction sliding, you lose all your strength. It actually does sustain its strength over that deformation for quite some time. So I think that's a huge benefit that came out of these technical updates. So these are just some bullet points on things that I already mentioned, but as I mentioned, we use an overstrength level flexure capacity. The factor that got us to that overstrength is 1.15. That worked pretty well to capture the strain hardening and material overstrength. So again, we're using, instead of just the flexural yielding capacity, we're using 1.15 times that to determine the shear associated with with that flexure behavior, and then see is it governed by shear or flexure. I think, yeah, I already mentioned the aspect ratio thing. So again, generally speaking, you'll calculate the strengths directly. Oh, I guess the nuance here that I didn't mention is that we recognize that a lot of practicing engineers do rely on aspect ratio as much as they can. And we did look at, can you just look at height to length ratio and determine whether it's shear or flexure controlled? And the correlation was very weak. You had a really hard time sifting out the appropriate failure mechanism based on just aspect ratio. But the concession that was offered is that generally speaking, if you had a very squat wall, so height to length of less than 1, then you tended to be not flexure controlled. So you could either be diagonal shear controlled or shear friction controlled, but you typically were not flexure controlled. And we do say in the recommendations that you can assume it's not flexure controlled, it's governed by some shear mechanism if you have a very squat wall effectively. But generally speaking, if you're setting this up in spreadsheets and those things, it's easy enough to just calculate the strengths and figure out the controlling mechanism you would expect. All right, outside of classification, we dug into the wall stiffness. I think every cycle back from all the way, maybe before 4113, I actually led some updates on wall stiffness updates in ASCE 4117, and then now it's changing again. So I apologize for the changes that keep happening on stiffness. You'd think we got it down, but I'll say that going back from ASCE 4106 onward, initially, if you all look back that far, we had a crack stiffness modifier of 0.5. We actually recommended during the 4117 change cycle that it actually go down to 0.25 EI. And that was felt that it might be too low for people, and people may not be used to that. And furthermore, in a linear analysis, people are using that stiffness to determine demands, and people were worried about underestimating the demands and being unconservative. The reality, though, is that ASCE 41, albeit it's not perfect, is really intended to be a displacement-based analysis procedure, or the procedures in Chapter 7 are really all based on displacement, or trying to estimate the displacement appropriately. And so with every version of the standard, I think we've gotten closer and closer to estimating the stiffness that would then tell you the right displacement. And then if you believe the kind of conversions you would have from a nonlinear displacement over to forces, then we should be capturing that appropriately with a better stiffness model. So that's what we did here. The other issues with that stiffness is that it didn't deal with some of the other variables, as we talked about earlier, with non-rectangular walls or axial load variation. There was some commentary that tells you how you can maybe do that in ASCE 4117, but there wasn't really a table that offered that. As many of you know, for columns, there's a table that tells you how stiffness would vary based on axial load, and that stiffness, that similar type of table is now offered in this technical background. The other thing that we looked at is whether you wanted to consider the wall cracked or uncracked. There are most cases, if you actually calculate the cracking moment strength and look at the demands in a high seismic region where we're worried about nonlinear actions and high seismic hazards, usually your walls are going to crack. Basically, all the walls in the building are going to have some level of cracking. But it can be the case that in a taller building, your upper stories may have very little moment demand relative to their strength, and you may be able to see that those are uncracked. So there are some suggestions, some technical recommendations for uncracked walls now, just as well as cracked walls. So I think that's a benefit if you do want to take advantage of that added stiffness. Excuse me, and you don't have to. It's always permitted to use the crack stiffness modifiers because you're going to be conservative on the displacement side, but it allows you a recommendation in order to do that if you wanted to capture the increased stiffness for uncracked walls. And this is how we do that. So if you look at on the right here, there is a pretty big scatter when you look at axial load ratio of a wall and then try to determine the the effective stiffness or EI of the uncracked wall relative to what you would calculate based on the gross EI. But you can see there is some correlation there, and the correlation is stronger for cracked walls. The reality is that when it's uncracked, you actually do get some cracking typically because of the either the shrinkage that happens during curing or temperature variations. You do tend to see some cracks. So we're saying it's uncracked from a demand perspective, meaning there's not flexural cracks that are happening from your demand. You haven't exceeded the rupture strength of the concrete in tension in that flexural action. However, you may have some reduction in your gross moment of inertia because of some of that cracking. And then you'll see that there are some that are actually really high. And the reality is in that initial portion of your backbone, there's a lot of sensitivity to the modulus elasticity. And anybody that's tried to use the ASTM test for modulus or any other methods, you'd find that there's quite a bit of variation in modulus for concrete, especially in your early portion of your curve. So anyway, that's what's going on there. But generally speaking, so the curve on the left is just showing what you would expect in this case, maybe for a trilinear type curve. If you have very little to no cracking early in your curve, then you get cracking, you get some reduction in stiffness, and then ultimately yielding. The red then would be kind of an idealized uncracked curve. So that would be allowed for a wall that you determine is uncracked in flexure, meaning the moment demand is less than the cracking moment of that wall. There's a table here then that offers that correlation to axial load. As you saw from the plot there, that there's not a hugely strong correlation, but there is a trend there. And so the technical recommendations were to allow basically between 0.5 and 1 for a quote unquote uncracked wall. Then for cracked flexural stiffness, this is probably more in line with what people are familiar with. And this is a stronger correlation, as you might expect, to axial load. So you can see that you can end up with very low stiffness, effective stiffness relative to your gross moment of inertia there, down at around 0.2 or even less. And then that basically goes up the more axial load you add up until you reach a peak of, we wouldn't expect to do more than the gross moment of inertia. So ultimately we ended up with a table that gives you that trend again for axial load ratio relative to your crack stiffness. And then in the technical updates, we actually dug into it further. The reality is it's not just axial load, but primarily your vertical bars or your flexural bars would also contribute to that stiffness. And there's this whole concept for constant yield curvature. So for a given cross section of a wall, you'd expect that the yield curvature is fairly constant. And that's been pointed out by a number of researchers in the past. And that's actually documented to some extent in the commentary, as I mentioned, that was added in 4117. But this allows a more, I guess, practical implementation of that. So you can pull it from a table. So there's a more detailed table that's offered that actually considers both the axial load ratio and the vertical reinforcement ratio. And generally speaking, as you increase axial load ratio or you increase vertical reinforcement ratio, you're going to see an increased effective stiffness. For shear stiffness in the past, you depending on your familiarity with the provisions of ASCE 4117, you may be aware that there was a 0.4 EA that was what was permitted or suggested in the provisions for the shear stiffness. And some people looked at that 0.4 and thought, oh, that's the cracking modifier for shear. Actually, the reality is it was put in the form of EA, but we know that shear is more of a shear modulus that determines the stiffness rather than modulus of elasticity. So there's a conversion from modulus of elasticity, which we typically put in our analysis models, to your shear modulus. And that would depend on the Poisson's ratio that you assume for concrete. But I think it's if you assume a 0.25 Poisson's, you would actually find with a gross shear stiffness that 0.4 EA is what you get with that conversion from shear modulus to modulus elasticity. So that was actually that 0.4 EA was basically no cracking assumed. It was basically a gross shear stiffness. And we looked at that, and it's actually more akin to flexure controlled walls, albeit you see cracking later in the backbone curve for shear controlled walls. But in the same fashion, we have an uncracked shear, so meaning your shear stiffness associated with a shear demand less than the shear cracking strength. In the backbone curve for shear, which we'll get to later, it's basically it's actually a trilinear curve for shear because it's a bigger contributor along the backbone than for flexure, where it's basically negligible. And basically, it's the concrete contribution to shear strength. When you exceed the concrete contribution to shear strength, which ACI 318 typically takes as 2 root F prime C, you'll find that you generally expect cracking to start happening in those diagonal struts and the cracking that we saw from the experimental walls earlier. And so on the left there, again, it's a fairly weak correlation, but we ended up kind of using an average of that for uncracked shear stiffness. And then when you are cracked, which again, if you're shear controlled, that would be what would be expected, obviously, because it's shear controlled and it's going to be the more common condition. Then you similarly, you don't have a huge variation along the length. So we ended up going with a 0.3. You can see that there's a little bit of a trend there if you plot the shear divided by the area times root F prime C, but it's a pretty weak correlation. So the project technical team said, why don't we just average it out? And for that, we'll use, I think the recommendation in this technical update was 0.33, or basically a third of the gross shear modulus. So final recommendations that came out of the technical background here in this FEMA P-2208 document were 70% gross shear modulus for uncracked. Again, as I mentioned, there's a little bit of cracking that occurs from things that aren't having to do with your seismic demand. And so you'll notice that if you convert that to your kind of EA type format, it's not 0.4 E anymore, it's 0.3 E. And then for crack shear, we would expect more of a reduction, and that ended up at 0.15. So again, about a third of the 0.4 that you're probably used to seeing. All right, now to get into the actual modeling and acceptance criteria, we start with flexure controlled walls, and the order that's listed here is actually the order that the project technical team carried out. So it fell in this order. And we first started looking at the fact that flexure controlled walls are really an important behavior. And even though there's an update for shear controlled walls in the ASCE 41 2006 supplement, there really wasn't anything that updated flexure controlled walls since the very early predecessor documents. So if you go all the way back to FEMA 356 and before that FEMA 273, then you'll find that the flexure control wall criteria are basically the same from the 1990s. So that was something worth revisiting. It's been quite some time since that point when those were developed. And also there's an opportunity for really looking at this big database and finding how well we correlated with those backbones, based on the actual data. And then ultimately, there are also these questions, as I mentioned earlier, what happens when you don't have just a rectangular wall, but you have a flange or a return wall? What about when you have really high axial load that in the earlier provisions, you basically just, the statement was that you can't use the wall or you have to treat it as force controlled. And then what about when you have really low reinforcement ratios? Because there were cases where you have existing buildings that really didn't have the reinforcement that we'd like to see today. And at some point, again, you had to treat it as force controlled. So the issue with those force controlled actions is that you came from having maybe little but some deformation capacity pass yield to all of a sudden it's a step function where now you're force controlled and you basically don't allow any inelasticity. You can't even go up to the average strength that you'd expect. And that becomes really difficult to deal with in an existing building. In a deformation controlled wall, you can degrade, especially in a nonlinear world, right? You can degrade the backbone and capture that. But if you're saying it's truly force controlled, you'd have to limit your drifts in your retrofitted conditions such that you never actually get that wall to yield. And that might be less than 0.5% drift, very, very low drift ratios, and wasn't feasible for a lot of buildings. So what we ended up with was this updated backbone. It looks pretty familiar. I'm imagining, to anybody that's familiar with the standard, you'll see that the general shape of the backbone looks similar. There were some updates in ASCE 4123. I'll just mention that actually went beyond this, and they actually have another portion of the curve that go after. This is the lateral resistance or the lateral strength versus deformation. And at some point, you actually lose all your lateral strength, but you may not necessarily lose your vertical load carrying capacity. So there's potentially another portion after you go to zero that ASCE 4123 considers that would say, hey, you haven't actually reached your class prevention limit, or where you would lose vertical load carrying capacity. In the 369 curves that you see, well, what went into ACI 369 and what came out of the recommendations of this document, you can see that the backbone basically ends at that point E, the big E. And for walls, it actually is the case that when you've gotten that far out, you pretty much have lost a huge portion of your concrete. And it's about that point that we tended to see vertical load carrying capacity was lost as well. Albeit I tried to push for seeing how far beyond that point we could go. It seems like there's not a huge amount of data to support going beyond that point for concrete walls. The other big update that I'll point out is that rather than the A and B parameters that you see for plastic deformation capacity on the left, so you see that those points, the lowercase ANL and BNL, they start from the yield point, whereas on the right, it's total deformation that's listed there. And that was already defined in the standard, but but the backbone that's used as the basis for the wall modeling and acceptance criteria is now total deformation rather than plastic in the past. There are a couple reasons to do this, but one is that I just shared that we keep updating the stiffness provisions. So if there's ever an update to the stiffness provision, the effective stiffness up to yield, you would actually find a different yield rotation associated with those stiffness provisions. So if you use the plastic deformation capacity on the left, every time you update stiffness, you'd actually have a different ultimate deformation capacity. And the reality is that the database and the relationship that Saman and team were able to identify was really well correlated to total deformation capacity. And so we didn't want that point to shift. There are also some other good reasons, excuse me, to use total deformation capacity. In terms of modeling, if you do a fiber model, it's usually easier to monitor the total rotation as opposed to some point that you define as yield. So for conforming walls, I guess for flexure, there are two different conditions that we said. They're either conforming walls or non-conforming walls. Conforming walls would be ones that we think are generally meeting the intent of ACI 318 for special wall provisions. They don't necessarily need to meet those provisions exactly. There's a little bit of a relaxation, one with the recognition that these are existing wall buildings, and that a relaxation would be good because you almost never meet the full requirements of the special detailing requirements in ACI 318. Excuse me, but also recognizing that when it comes to bang for your buck, you actually, if you get most of the way there on those detailing provisions, you actually capture pretty well the deformation capacity that you'd like to capture. There's very little extra deformation capacity you get beyond a certain point of confinement ratio or some of these other things. So those there's an actual bullet list that came out of the recommendations on telling you, hey, this is when you're conforming. This is a big step relative to what was in ASCE 4117, where I think there was a statement that just said, hey, if you meet 75 or 80% of the ACI 318 provisions, you can say it's conforming. And obviously that there's wide interpretation of what that could mean. If you're not conforming, then you're non-conforming, and then you generally use the non-conforming table. But I'll bring up a caveat that this does not apply to inadequate lap splices. I mentioned earlier that this database did not consider inadequate lap splice walls, and the intent was not to say that if you don't meet all these requirements, you always get to you always get to use the non-conforming table. We're actually talking about a code interpretation. I can't remember exactly what it's called, but ACI 318 actually did this recently for some of their provisions, and ACI 369 is considering the same thing to basically allow for a question to be asked to ACI. This came up in a peer review, not actually one of my projects, but one of my colleagues asked me, and one of the requirements on conforming walls is we say it has to be adequately lapped, and so I can see the interpretation to that it sounds like was being made on that project, that if you don't have that, then you're non-conforming. Generally speaking, if you don't meet these, you're non-conforming, but I do want to highlight that if you don't have adequate laps, you still have to go back to the broader provisions that govern in the section 3.5 or whatever it is in ACI 369. So then we get to the actual modeling recommendations. And one of the really interesting things that came out of that database analysis, the data analysis that Saman and team had done, was that in the past, the table was basically dependent on shear demand ratio, shear stress basically in your wall, and axial load. And when he had looked at axial load as a parameter for deformation capacity, Saman was finding a fairly weak correlation to axial load. I think there's, again, some trend, but it's a fairly weak correlation. So in his dissertation work, and then ultimately what got refined in this project, he came up with this sort of lambda term, or this relationship of the neutral axis depth. So that's the C in that equation on the horizontal axis there. The neutral axis depth times the length of the wall divided by the thickness of the wall squared. And what really was showing up here is that the neutral axis depth mattered, because the neutral axis depth tells you, one, how fast or how much do you expect crushing of the wall, and that would be influenced by both your axial load, which again in the past was captured as its own parameter, but also the vertical reinforcement ratio and the strength of concrete. So it captures a number of different variables implicitly when you calculate the neutral axis depth. And then the other thing that matters is, so it's the neutral axis depth relative to the thickness. So if you have a pretty thick wall or a pilaster or something like that relative to that neutral axis depth, you're going to be better off. The other thing that matters is the cross-sectional aspect ratio of the wall. So what was found, and this is pointed out by other researchers in the past, Laura Lowe's, who is actually one of the working group members, had a lot of work on this, and others, that if you have a really slender cross-sectional aspect ratio, you tend to find, so you know, in an extreme case, say you have a 100-foot long wall with, you know, an 8-inch thick thickness throughout the wall. When you start to get that demand on the flexural compression side, along with you also have these diagonal stress that are coming in from the shear, you actually get this unzippering that happens, if I'm just describing it correctly, where as soon as you get crushing at the end, a lot of the length of wall gets lost on concrete crushing. And so the other term there is the length of the wall over the thickness of the wall. So if you combine those two, you get this lambda term, and it's the length of the wall times neutral axis depth over the thickness squared. This is pretty informative. One, the coefficient of variation was really good. If you've ever looked at concrete strength relative to experimental data, or any of, you know, shear strength, for example, you know that there's like a big scatter plot and then you have a line kind of under that. The goal here was really to get the mean deformation associated with this parameter E, or really the ultimate deformation capacity. And the coefficient of variation of 0.22 is really good for concrete. And actually, you know, relative to even the steel provisions, I've seen some similar plots on the WOOF connections, for example. This is, I think, some of the best I've seen. So this is impressive. And it also provides a little bit more, I think, understanding of what's important in the wall deformation capacity. So I mentioned the behavior that's going on there. you can actually use that in the back of your head as you're analyzing these wall buildings and have a sense of whether the deformation or ductility capacity is better or worse. Ultimately, then, that found its way into this recommendation table. The other parameter there that I didn't really mention is outside of that lambda term, which is on the far left column. The shear stress is basically in there in the middle column. So the shear associated with flexural yielding is that VMCULT-DE term. Don't ask me why it's so long. That shear associated with flexural yielding over ACV over root F or times root F prime C is basically your shear stress ratio at flexural yielding. And then what looks to be a WV, it should have been an omega. There was a font thing going on there. Is the dynamic amplification ratio or dynamic amplification factor. So we know that there is some dynamic amplification in shear up the height of a building, and so that accounts for that. So those first two columns are pretty much in line with what one you might expect already from the past provisions, and then what I talked about. The third one there is overlapping hoops, and you can see that there's not a huge change in the deformation capacity in the DNL that's listed there relative to overlapping hoops, but it does make some difference, particularly when you have the higher lambda values. So when you're more likely to experience crushing, that overlapping hoop parameter does start to matter, and so that in general, existing walls probably won't have this, but it's one more parameter to consider, and especially if you're understanding wall flexure deformation capacity, you should understand that does have some influence. And then you can see, although there's some influence on the DNL parameter, it wasn't big enough to include in the other parameters that govern our backbones. So if you look on the table on the right there, or the portion of the table over to the right of the screen, you see that you still have effectively that lambda ratio, but then you also have axial load ratio. And interestingly, shear doesn't show up anymore. It's really the lambda in combination with axial load. And that's what determines both your ultimate deformation capacity. So when you actually lose total load carrying capacity of the wall, and also your residual strength. And that sort of makes sense because usually that means that you're crushing the wall. So axial load does tend to influence that crushing and whether you truly lose all that concrete along the length. There is then a peak strength point. So one thing that's probably worth noting on this, beyond yield. So you have the first portion of your backbone, which is determined by the effective stiffness we talked about earlier. You have your yield strength that you capture with your flexure capacity from ACI 318 and basic mechanics. And then you have this big point C, or uppercase C, that is the ultimate strength associated with flexure. And that would generally be, that's up here on the curve. So that would generally be higher than your yield because you have strain hardening and those things, but it's not just the steel strain hardening that affects things, it's actually concrete overstrength also. So this is a nuance that is probably lost if you don't read through these technical recommendations in depth. And it's worth mentioning because we do allow basically one factor, 1.15, to understand the difference between your ultimate peak strength and your yield strength. And that's not only considering the strain hardening in the steel, but it's all other sources of material overstrength that lead to that. And interestingly, we actually found, at least this is what was reported by Saman and the folks really doing the data analysis, is that the 1.15 factor actually corresponded better to the observed strength in the walls than actually trying to model a fiber model with strain hardening in the steel. Again, they're multiple factors at play, so it's not just the strain hardening. So worth mentioning in case you're considering your fiber model, and you do have the ability to use an overstrength on the steel to account for this. The provisions talk about that, the recommendations talk about that, but it's actually permitted to use just a factor of 1.15 on your calculated moment strength, and that's the reason that's permitted. The other thing that we did, I mentioned this briefly earlier, that you had an issue. There were some updates in I think the version from ASCE 4113 and ASCE 4117 that said you can go down to 0.00015, excuse me, reinforcement ratio instead of the traditional 0.25% or 0.2% that was in there previously. Often these walls in our existing buildings have substantially less reinforcement ratio than the 0.25% that we'd like to have as a minimum. And there is always an issue where you'd have a step function in that term where all of a sudden you're force controlled. So I was one of the loud voices actually in the working group that really pushed hard for saying we shouldn't have a step function ideally. We should offer recommendations for when you have lower reinforcement ratios. And so generally speaking, there's a little bit more lenience or variability that's offered now, and you can go all the way down to 0.1%. But it does, there's some footnotes that got added ultimately in the provisions in ASCE 41, and you'll see why in the technical background in this FEMA document, that there's a little bit of nuance there when you get lower reinforcement ratios and a low lambda, you can actually have lower deformation capacities than you might otherwise expect. And I think that has to do with when you have a really low lambda, you typically have a very low vertical reinforcement ratio. And so just like in ACI 318, when we want a minimum flexural reinforcement so that after your cracking strength is reached, you don't suddenly try to transition that demand from the concrete to the steel and not have enough steel to where you get a rupture. I think that's generally the effect that we're seeing. And so it's a relationship of not only the reinforcement ratio, but also that lambda term going down. There's actually an interpolation you have to do in order to find the deformation capacity. So you'll actually get a hit. You don't just get a lower lambda and a benefit as you do with reinforcement ratios that are higher. You actually get a hit when you have low reinforcement ratios. So you should be aware of that. All right. Really, then the culmination of all that is found its way into these tables. You can dig through those in more depth in the document. I won't go through them in too much depth here. When it goes then from modeling recommendations to acceptance criteria, there is a realization that we don't want to go all the way up to that mean modeling. This is really intended to be the median expected modeling parameter or deformation associated with those different points on the backbone. So in terms of modeling, we want to try to get the median, but then when it comes to acceptance criteria, the goal is to back off of that a little bit and offer some level of conservatism. That's generally the way that ACI 369 standard deals with things as well as ASCE 41. And so the recommendations in the FEMA 2208 document were for backing off the acceptance criteria as listed in this table. I think ultimately this is also where there's some variance on the provisions that ultimately got passed in the standard, but these are the recommendations. And you can see that, these are pretty similar to what ultimately went in there. Coming out of the technical updates though, there are a couple approaches that were talked about. The question came up, do we just give these equations when you go we're going from our nonlinear world, which is real, into now a linear acceptance criteria if people are using linear procedures? How do we go about doing that? The most direct way and maybe correct way is to just take those parameters that came out of the nonlinear recommendations and then apply these factors based on the rules in ASCE 41 and further some of the things in ACI 369 to then get an M factor. So you're basically backing off the acceptance criteria, one for just a little bit of conservatism relative to the coefficient of variation and dispersion, but also recognizing you're doing a less sophisticated analysis procedure when you do linear procedures. But this looks a little bit more complicated and people don't have a gut feel for what this means. And there was some desire for the folks using the linear procedures to say, what is just the M factor number? Give me a table with numbers. So there are two different options that were recommended. You can either use the equations, or if you want table numbers, here are some table numbers. I did notice also that these table numbers varied a little bit. They actually got a little bit better in the provisions, and that mostly had to do with the assumed theta y that you put in there. So basically to get to an M factor, you're taking the ultimate deformation capacity and you're dividing by the yield deformation. And so in order to do that, you have to assume a yield deformation for all these different conditions. So the approach for that was a little different, I think, when it went to the standard, but there was an assumption that was embedded in informing these tables, and you can look into that in the document. Ultimately, you can see, generally speaking, there is quite a big progression, or I would say better performance that we're getting, I guess better M factors in this case, that, when you look at the linear procedures that you get for flexure controlled walls. So the ones that came out of the recommendations are these green and purple and I don't know, dark brown type colors. The ones that were in ASCE 4117 are in the red and the blue there. And you can see that in almost all cases, they're either equal or better in the updated recommendations. So these should benefit your analysis if you're utilizing these recommendations. When it goes to shear controlled walls, a lot of the approach was similar. We binned the data to the shear controlled walls, as I talked about earlier. As I also mentioned, we were looking at total deformations. This is actually similar. It was already the case for shear in the past provisions, but we also added this recommendation for a peak strength. In the past, it was assumed that the yield and the ultimate peak strength were the same. There was a recognition that from the database, there is some overstrength that's observed there. So that's recognized here now. And in addition to the yield strength or kind of the median strength in shear, there's a look at the cracking shear strength and some more sophisticated equations that are captured there. So it used to be that you just assume 0.6 times your shear strength for your cracking strength in your trilinear backbone and a shear controlled wall. And now there's actually an equation there, and it's essentially associated with again, the concrete shear strength contribution to your diagonal shear strength. And one of the things I'll recognize or note here is that for a flange, what we call a flange wall, this would mean that you have either a return wall or kind of a flange cross section. There's actually a bigger strength on your cracking that's associated with that return wall, and that was observed pretty substantively throughout the database. The way we define flange wall is basically if the ratio of the flange moment of inertia to your rectangular moment of inertia is greater than 1.5, then you're allowed to call it a flange wall, and you actually get a benefit on your cracking strength. It cracks later, essentially. And I think that the main thing there is you're seeing that as you're going toward the flange, particularly, you have more of a nodal reaction, if you think of a strut and tie type concept, that allows for crushing to occur later, and I guess diagonal cracking to occur later. Really, not the crushing, yes, but also the diagonal cracking. I guess it really benefits to have a flange there on the cracking strength. So yield strength, you can see a pretty good correlation in the trends there on the tested strength versus the recommended strength coming out of these technical recommendations. And this was interesting. So what we found is that it was, when you calculate ACI 318 shear strength equations, you actually did pretty well when the wall was close to being on the borderline between shear controlled and flexure controlled. If you think back to that earlier chart of all the different wall conditions, if you're kind of where that vertical line is, where you're crossing over from shear to flexure, the ACI 318 shear strength equation does pretty well. But as you get closer and closer to, I guess as you get more and more shear controlled, more squat or more shear controlled, as you might think, then you actually get an overstrength relative to the ACI 318 strength equation. And so this term in parentheses ahead of the shear, this term here, VC wall 318E, is the shear strength from ACI 318. This factor actually amplifies that. And this term here is, again, the shear strength from 318 divided by the shear associated with flexural yielding. So essentially, the more squat you are, the more shear controlled, the bigger this amplifier becomes. And what you'll find is that becomes greater than 1 up to a limit of 1.8 in the case where you have a very squat wall. But when you're pretty close to being shear flexure controlled, between the two crossing over, this will kind of navigate toward 1.0, and you'll find you pretty much get the ACI 318 shear strength equation. Then for the peak strength, similarly, we do offer some overstrength, and that's a change from the 318, sorry, ASCE 4117 provisions, where we assumed the same strength for peak and yield. Now it's a 1.1 factor, and you can see there's a decent correlation there. Again, generally the 1.1 fit pretty well for all those conditions. And then this residual strength also it depends on whether it's considered a flange wall or a planar wall. So you can see you get a little bit different residual strength ratio, excuse me, depending on that condition. We talked about uncracked and cracked shear stiffness. This is, I think, just reiterating that ultimately there was a recommendation for cracked shear and uncracked shear. So the thing is that we had to incorporate this also in those updated backbones. So in the flexure controlled provisions, and there's a little bit of a disconnect, but arguably for a flexure controlled wall, it's maybe more fair to say that there wasn't really any shear cracking. In the shear controlled wall provisions, we did incorporate the shear cracking, and so that informed some of the yield deformation capacity and those things. So ultimately then we ended up with these are the drift capacities you get either at class prevention or life safety, and you can see that the proposed values in this case generally still again they're equal or better than the ASCE 4117 provisions. But the big thing is you'll notice it's not quite so much of a step function between these different conditions. You have more of a linear kind of line that goes through that. Granted, it does vary. And also ultimately your higher end does get quite a bit higher. So for the good conditions, you do get quite a bit better deformation capacity. Similarly, we offered both the equations and actual table values for the M factors. We had to embed the assumption for yield deformation into those, but you can see all that background in the document. And then finally, I want to get to shear friction and then some general modeling stuff. So I know I'm coming up on time here. I just want to quickly go into shear friction. The reality is shear friction is it always was sort of embedded in the standard, but as I mentioned earlier, it really was treated as a force controlled action. And now we actually have some data to give recommendations on the deformation capacities and those things. And in doing that, we also saw that the strength may vary a little bit relative to the shear friction strength provisions that are in ACI 318. Those strength provisions tended to or mostly came from data where it was a push-off shear test, like pure shear. And in a in a wall that's a cantilever wall, you get flexural cracks that develop on the tension side of the cross section. And that influences that shear friction coefficient, if you will. So you kind of, in a cyclic loading condition, your influence of the interface, whether it's roughened or not, and those things actually is much less significant. So we actually find there's a different mu that's recommended for the shear strength, and generally the difference in mu's is much less than what you'll see in ACI 318. And generally we saw a little bit lower strength. This is the backbone that was developed for shear friction. The idea is that you model your shear material and you basically have no flexibility in shear friction or sliding until you reach that strength. And then at that point, if that's what governs in your condition, then that takes over. And that's where everything beyond that point would be governed by this backbone. But the reason that this starts at 0 is that up until you reach your sliding strength, you get essentially no deformation or no flexibility from the sliding. It's not really till you initiate sliding that starts to occur. The shear strength equation, the form that it took is actually very similar to the shear strength, the diagonal shear strength equation that I showed earlier. So this shouldn't be much of a surprise. But as I mentioned, the mu that's embedded there. So basically this is the shear friction strength from ACI 318. But you'll see that, so this is essentially the same. Some of those limitations are actually explicitly not needed in this equation that you find in ACI 318. So it's a little bit more simple. You can use that. You'll find that the mu's are a little different based on my comment earlier. And then you do again get this overstrength relative to ACI 318, again, depending on how squat are you or how shear controlled are you. You're also allowed to use just the simplified shear friction equation there. There is a little bit of an overstrength when you look at the overstrength relative to yields, so that is captured there again with the 1.1. and then their recommendations for the residual strength. So ultimately, you end up with this table. These got changed a little bit in the ultimate provisions, but I actually think that this is probably a good number. And we'll be looking at again this next cycle. This got relaxed a little bit, or made a little bit more penal in the standard ultimately. But the technical background is here for you to look at. And granted, there is a recognition there's very little data on the actual ultimate point for shear friction controlled walls. Last thing I'll comment on briefly here is that there is some updated guidance on modeling, and you'll find more extensive guidance here in this FEMA 2208 document than you'll find in the commentary, because this is where it gets a little bit more esoteric if everything I commented on earlier wasn't esoteric enough. But this really talks about how do you do fiber modeling, how do you consider, if you're not just doing a plastic hinge, a concentrated hinge, how do you consider fibers in your model? And how do you also consider things like asymmetric wall conditions and some of those other things? So hopefully there's some good guidance in there. The other key thing that I'll mention is that if you're using a fiber model, it's not as simple as just putting in a stress strain relationship for your fibers. You really need to consider your mesh and consider what is your global load deformation envelope, and is that matching the recommended load deformation envelopes or backbones that come out of these recommendations? Because there's a lot at play that's not only dependent on your fibers. There's shear flexure interaction, as I mentioned. There's mesh dependency in any continuum model. So this document offers some good guidance on how to consider some of that. I guess that's included more so in the bullet points here. There's also some recommendations on the shear friction. As I mentioned, it's a little bit nuanced. So if what I mentioned briefly here wasn't enough for you, you can dig in deeper in the document. And that's really all I have. And I'll pass it to Mike here for any Q&A and some of these other items.
Thanks, Garrett. We appreciate the presentation you made. We've got about 14 minutes left maybe for questions. Before we dive into that, I'm going to take a moment to summarize a couple of important points that participants may care about. For those of you who are eager to receive your PDH certificate, note that they're only provided for those who registered and participated in the live webinar, not in a recording. You can expect your certificate within the next 4 weeks. Due to the large volume of participants, please understand that we can't make exceptions to our PDH policy. So now we'll try to address as many questions as we can. I've organized the questions that we've received, Garrett, based on some general topics. So let's start generally. Were speed core walls investigated? A couple of folks asked.
Good question. I know that's a good one as we're progressing our technology and our innovation. The answer is no. These walls, as I understand, although the 1,100 walls in the database were more conventional concrete walls, but that would be, one of the considerations there is these are typically, the provisions that we're recommending on were for existing buildings. So there may not be as many of those speed core walls out there that exists already. But as we move forward, obviously any new building that's actually built becomes existing. So that might be a good thing to look at in the future. But no, not at this point. They weren't considered.
Okay, thanks. We've got, because we have participants from all over the world, a general question that you might be able to answer. Do ACI and ASCE have provisions for seismic design of precast walls?
Yes. So I'll be totally frank and transparent and admit that the precast provisions in ASCE 41 and then what you'll find in ACI 369.1 are fairly weak. There are provisions in there, but they have not been looked at for a long time, and they're pretty general. But if you go to there is more collaboration between ACI and then PCI, and there are documents out there that are more extensive on precast. I will admit though that that's an area that could be developed further in ASCE 41. We don't have as many existing precast buildings as we do cast in situ or cast in place, but they are out there for sure. I was just in New Zealand, and precast is a huge topic for them. And so I will say that there's more collaboration, I think, going on internationally, and I'm hopeful that we'll pull some of the best information from all of that work going on, and hopefully see that in the future. But not a ton in there. There are provisions that exist.
Okay. Just a general question about the testing that was used to support the recommendations. Can you comment on the size and thickness of the specimens that were tested, or on the reinforcement for shear and flexure? How narrow or broad were those parameters?
Yeah, so these are walls that are tested in a lab. So there are limitations to most labs that in terms of the actuator capacities and how basically strong they can push, right? So I think there are limitations. Saman would have a better sense on the specific numbers, but generally I think these are walls that are in the thickness range of 3 or 4 inches up to maybe 8 inches or so. Um, there were some walls just for color. Um, the scale of those walls in the database is probably, not typically full scale, but maybe half or less scale, and generally smaller walls. But I was part of a test program, for what it's worth, that Simpson Strontai put together for really full scale walls that were squall walls. And it's just worth noting that we actually use these recommendations to try to predict some of the behavior. And the goal for that one was more related to FRP, but there were control walls with just concrete. And these recommendations did very well at predicting the behavior. I was actually amazed at how well they performed. So I think they're relevant, but again, there's limitations on the labs there. In terms of reinforcement ratios, they ranged quite a bit. So they went all the way down to, I think I noted in one of those slides that the previous lower limit was 0.0015% reinforcement ratio, and they go below that down to 0.001 or so. So almost what you'd expect with like a plain concrete wall. And then they go up pretty high where you have quite a bit of boundary steel and those things. So the reinforcement ratio, I would say, varied quite a bit. Maybe there's a good amount of data there.
Okay. Next question. How do we determine whether to treat an element as a wall or as a column?
Excellent question. Yeah, that is something that we are looking at. I'm specifically involved in a working group that's looking at that for the next cycle, more in the ACI realm. If you're interested in that stuff, I definitely encourage folks to get involved in both ACI and ACE in some of these efforts, because we need more bandwidth. But yeah, that's actually, it's not explicitly dictated in the standard. There are some recommended, like, so if you look at the database, generally speaking, the database for walls consisted of cross-sectional aspect ratios of 4:1 or greater. So generally these are fairly rectangular walls. Again, 4:1 in terms of length to thickness. If you then look at the column database and inform the provisions in ASCE 41, it's usually actually square columns. There are very little rectangular columns. They're typically 1:1 length to thickness ratios. You might have some that were a little bit more rectangular. So there's a bit of a gap in data between what you would call a column and the database that informed that versus this database that informed the wall recommendations. And we're looking at that because if you call it a column and you plot the backbones, you'll get in some cases quite a bit different result than if you call it a wall. Generally speaking, though, I think the best parameter is your length to thickness ratio. And you could argue maybe be more conservative if you're not sure. There is some language in another FEMA document. I think it's FEMA P 2018 for non-ductile concrete. Mike, I don't know if you know or others if that's right, but I think that's the right number. They I think recommend in that procedure a 3:1 aspect ratio, and there's some language in ACI 318, but there's not an explicit provision in the standard or in these recommendations. But there are details on the database, and again, it's generally 4:1 or greater.
Okay, thank you. For the next one, maybe you can go to slide 24. It's a good question and I've done a little homework while you're presenting. On slide 24, the question is whether in the right-hand table, the row, the inequalities on row have been reversed. So it says greater than or equal to 0.01 and less than or equal to 0.03. I confirmed that the table that is here is as it appears in FEMA P-2208. But the table 7.3-1 in ASCE 41 is not that way. It is less than or equal to 0.01 and greater than or equal to 0.03, which might make sense, but I don't know the correct answer. So it would say if you are a low reinforcement ratio, you should have a lower crack stiffness. That's what 41 would say. This table has the opposite.
Yeah, I think you're right that those inequalities should be reversed, and these are recommendations, and that's one of the benefits of going through the consensus process. Is I think that was one of the things that we cleaned up or clarified. So in general, the idea is if you're 0.01 or less, then you'd use the 0.2, and if you're 0.03 or more, at least in that first row for axial load, you'd use 0.3. If you're in between, you would interpolate between those.
Okay, so it confirms, thank you, that maybe there's a typo in the FEMA document that got fixed in ASCE 41.
That's right.
Okay, so a general question about shear, is the dynamic shear amplification factor omega sub v the same as in 318.19 for consideration of higher modes?
Yes, it's intended to be the same. At the time that the consensus process, and granted, this webinar is more about the technical recommendations that inform some of that. The technical recommendation was really, hey, do the same that was recommended in ACI 318 because there's no reason that they should be different conceptually. At the time that that was then going through the consensus process in ACI 369, it was brought up that there was going to be some re-looking at ACI 318.19 and potentially changing that for the next version of ACI 318. So those that are familiar with all that probably know that ACI 318 2025, which will be, if it's not already released to the public, it should be shortly here. There was some changes. There were some changes that were made on the dynamic amplification factor. That is not incorporated here. The idea was let's be consistent with the consensus standard that is currently adopted or published. So the idea, it's actually something that was brought up for a code question also. The idea is that we're intending to be consistent with ACI 318, and there is the argument. So some of those changes on the 318 side had to do with expected material properties versus minimum specified, which is what new code uses. Those issues don't exist here in existing because we tend those specific issues because we tend to try to target the median expected strength for existing. So part of that goes away, but there were some other components that arguably could feed in here. But currently, this is based on the same procedure as ACI 318.19.
Okay, thank you. On slide 44, we have a question about how to interpret what we've got here. On slide 44, you show cracking strength models, and it's flanged versus not. And the question is, does this indicate that a flange served to disrupt the cracking?
Essentially, yeah. I mean, you could interpret it that way. The idea is that you get a higher cracking strength when you have a flanged wall. And so I think if you conceptualize your strut and tie behavior, you might find that there's some influence on the strut when you have that flange. And effectively, the outcome is that your cracking strength, if you were to idealize this as a trilinear curve, is higher or double in this case of what you would get for a rectangular wall.
Very good. When you were talking about the conforming versus non-conforming, you said that inadequate lap splices weren't explicitly updated, and I have had a couple of questions about that. One was, how would ASCE 4123 classify a flexure-controlled wall that meets the conforming detailing and has adequate lap splices near a critical section? Does it still is treated as conforming then or not?
If it does have adequate, was the question?
Yeah, adequate. I mean, the question is if it's at a critical section,
Yeah.
the new building approach might be different.
Yeah, so generally, so the overarching provisions for lap splices, hopefully I'm getting the section number right, but I think it's in section 3.5 of ACI 369.1. But in the broader provisions in chapter 3 of ACI 369, it tells you how you need to check adequate or inadequate. You'll find that in going through those, there's specific provisions for columns and beams. And then there's a general statement for other members. That general statement would apply to walls. So generally speaking, if the way those provisions work, if you have adequate development, then you are good. And one of the criteria for conforming walls that's in those bullet points that says you're conforming is indeed also adequate lap. And all that means is that you're meeting LD. You're not meeting, you don't actually need to go LS, and you don't need to extend beyond the critical section like ACI 318 says. You just have to meet LD. So the answer would be yes.
Okay, and the corollary to that is if the lap splices does not meet LD, would you consider the wall to be non-conforming?
Yeah, so that was the thing that I tried to highlight a little bit, is that it wouldn't mean that it's a non-conforming wall in terms of using that table. It means it's definitely not a conforming wall. You can't use the conforming table, but you still have to consider those overarching provisions that happen. Those govern the overall standard. They're not just relevant to walls. There are provisions in there for adequate or inadequate laps that govern everything. And those provisions that I mentioned would tell you that if you're inadequate, then your backbone needs to degrade right after reaching your strength. There's a reduce FY that you have to consider. It's an F sub S that's reduced based on the amount of development you do have. And then it would tell you need to degrade to a capacity of 0.2 times your strength at a ductility of 2. So that generally is what you'd have to follow. Now, how do you apply that to acceptance criteria and everything else? I fully admit that's something that needs some clarification in the standard, and that's something for next cycle. But generally, you can form acceptance criteria based on those provisions.
Okay, thank you, Garrett. We've reached time, so we appreciate your answering those questions. For you participants, please click the survey link that pops up when you leave. We especially appreciate your input on topics you'd like to see covered in future NEHRP, FEMA NEHRP webinars. That's how we plan out our webinar program. And you can expect to receive a follow-up email in the coming days with links to the recording, handouts, and survey again. On behalf of FEMA and the Applied Technology Council, I'd like to thank Garrett for his presentation, and thank you to everyone for joining us today. This concludes the webinar.
Thanks, Mike. Thanks all.